Hello, welcome back, Cosmic Hitchhikers. Today, we are diving into the ultimate its complicated relationship, general relativity and quantum mechanics. One is the king of the very big, planets, stars, and the fabric of the universe. The other is the queen of the very small, atoms, quarks, and the chaotic subatomic zoo. In physics, if you want to describe how the universe works, you need an action. Think of action as a rule book. It tells the universe how to get from point A to point B while being as efficient as possible. We have a rule book for gravity, Einstein Hilbert action, and a rule book for particles, standard model. But when we try to bind them into one volume, the pages catch fire. Here is the dirty secret of theoretical physics: infinities. In quantum field theory, when particles get too close, the math gives us infinite values for things like energy or mass. Usually we fix this with a trick called renormalization. Think of renormalization as a cosmic reset button. We subtract an infinity from another infinity to get a sensible finite number we can actually measure in a lab. It's sketchy math, but it works for electromagnetism. It's like clearing your browser cache so the website actually loads. But gravity is non-renormalizable. When you try to renormalize a quantum theory of gravity, you do not just get one infinity. You get infinite number of infinities. Every time you fix a leak, 10 more burst open. It's a mathematical whack-a-mole that never ends. The action becomes useless because it can't give us a finite prediction. Why does the math break? Because of the Planck scale. To give you some perspective, if an atom were the size of the entire observable universe, the Planck length would be about height of a tree. It's the shortest possible distance where our current understanding of space even makes sense. According to the Heisenberg uncertainty principle, as we zoom into these tiny distances, energy fluctuations become so violent that they warp space-time itself. We call this quantum foam. At this scale, the smooth trampoline of Einstein becomes a bubbling chaotic of mini black holes and wormholes. This leads us to the singularity problem. Inside a black hole, or at the moment of the Big Bang, you have massive gravity in a tiny quantum space. Without unified actions, Einstein's equation basically throw their hands up and scream divided by zero error, and the simulation crashes. So how do we fix the rule book? We have two main candidates. First, a string theory. It says, stop treating particles like points. If particles are tiny vibrating strings, they have a minimum size. You can't get to zero distance, so the infinities never happen. The catch? You need 11 dimension and a PhD in math just to say hello. The second one is quantum loop gravity. It says space isn't a stage, it's the actor. It suggests space is discrete, made of tiny quantized loop or atoms of space. Space isn't a smooth sheet. It's like a piece of chainmail armor. Both theories are trying to write ultimate quantum gravity action, but we are still waiting for one eureka moment that we can actually test in a particle accelerator. Finding this action is not just about winning a Nobel Prize. It's about reading the source code of reality. It's the difference between seeing the universe as a collection of random events and seeing it as a single beautiful symphony. So if your Python code isn't converging today, just remember, the universe's own code has been debugging for 13.8 billion years, and we are still looking for the syntax error. Stay curious, keep calculating, and I'll see you in the next dimension. Don't forget to like, subscribe, and let me know in the comments if the space is smooth or chunky.